Let's go through Lico 312, burst balloons. So we are giving n balloons index from 0 to n minus 1. This n is actually the length of this nums array. And each balloon is painted with a number on it. So this, for example, number 0 will be the number on the balloon i's value. So every time you are able to burst a balloon, and if you burst the ice balloon, you will get nums I minus 1 multiplied by nums I multiplied by I plus 1 coins. So you see that if I minus 1 or I plus 1 goes out of bounds of the array, then treat it as 1, just like a balloon as 1 on its left. Retain the maximum coin you can collect by burst all the balloons wisely. So let's look at the example. We have 3, 1, 5, 8. The optimal way we burst up the balloon is burst this one. So we'll get 3, 5, 8 for next round. And we'll collect the coin as 3 multiplied by 1 by 5, right? Will be this one. And the next round we went the way we burst is burst this. So we'll get 3, 5, and we'll add the coin as 3 multiplied by 5 multiplied by 8, right? And then the next one we burst 3, we're left 5. So that means because on its left there is no balloons, we'll treat it 1 as 1 to count, right? So it will add 1 multiplied by 3 multiplied by 5. And then the last one, you treat 2 ones on the left and right. So 1 multiplied by 5 multiplied by 1, right? So doing burst that balloons like this way will get the maximum score. So if you give us an array nums, ask what's the maximum score we can get. We'll see the time range is n is smaller or equal to 300. So for this kind of range, we can think about like O n power 3 time complexity can be this question can pass, right? So we thinking about for this question, how can we handle this? Actually, there are two approaches. One is greedy, right? Another is possibly we can think about dynamic programming. But greedy for this question, it's not true, because some people want to choose the smallest number, right? But the thing is, if we choose the smallest number, we cannot prove that this will always be the correct direction, right? Because, for example, you see this one, we choose 1 as the smallest, but the second, we are not choosing 3, we're choosing 5, right? So the greedy up, we should think maybe not a good way to do this, right? So we're thinking about whether we can do some kind of dynamic programming. So dynamic program is that for this kind of nums, there are 0 to n minus 1, right? So what we want is that we want to know what's maximal score for this kind of range or interval, right? So we can think about this may falling into the interval DP problem. So how can we think about those kind of substates? Is that for this kind of 0 to n minus 1, right? So we'll see every let's have DP I j represent those kind of maximal scores we get in a range I to j, right? So we burst all the blooms in a range I to j, which ij are inclusive ij, right? So if we calculate this one, the final state we want is just want to get dp0 a minus 1, right? So if we have this dpij, what is our substate? We already calculate. We can think about in this I to j, right? We consider there are two kind of scenario direction we consider. One is the first bloom we trying to burst. For example, k is from 0 to j, right? But for this one, if we choose this, it separate our blooms like this kind of I to j without k, right? But this kind of state like will not calculate because for the first bloom, the second bloom it can be on its left or on its right, right? On its right. But the thing is that we cannot separate these two parts. So we can think reversely, the last bloom left for this kind of range. So the last bloom left can happen from this kind of any I to j, right? So if k is the last bloom we burst in the interval I to j, then our score will have three parts. One is the dp I to k minus 1, right? That means this part already all are burst out use rate. And also dp k plus 1 to j, right? And this part are all burst out. And another one is dp the last one is just we left the one bloom k here, and the score we want to add is nums I minus 1, j plus 1, and multiplied by k, right? So it will have three parts. Then we just want to iterate the k from I to j to find the maximum. So the transition state. So we have dp ij will represent maximal score for interval score to burst all blooms from I to j, right? Inclusive. I'll say some people use exclusive for ing and add some kind of dummy on the dummy one, a dummy one at index before index 0 and after index n, right? That is another approach, but the thing is that I prefer to write code consistently, use always inclusive for the interval dp. So I write include ing, right? So we iterate all k, which is from I to j, right? So our dp ij will be max dp I to k minus 1, right? So the thing is that this k minus 1 should greater equal to I. And we should, of course, when we add this one, we need to have a condition saying if it's not, we'll not add this part. And add nums I minus 1 multiplied by nums k multiplied by nums j plus 1, right? So this one, if it is outbound, we also need some condition that it is 1, right? And add dp k plus 1 and j, right? So in the end, what is the final state? We just return dp 0 then minus 1, right? So doing like this, we will know this will be a transitional, a classical interval dp, right? So we can use the what we write. We can pretty much like a template to write this kind of question. So we'll write code into n equals nums of length, right? And we are going to have int dp equals new int and right? For the initial state, of course, we can write, for example, for int I equals 0, I smaller than n, I plus plus, right? And the dp I equals nums I minus 1, right? Of course, this we need to say if this I equals 0, right? It will be 1. And multiple by nums multiple by something, right? But for this question, we can have this kind of initial state here, right? But we can consider whether this initial state can be concluded in our the main function, the main code, right? So if our main code will include this condition, we don't need this state. Sometimes we need this one, like we want to see that whether those kind of palindrome, those kind of problem, right? We need this kind of state. But for this one, this condition is included in our transition functions. So what we do is that for int length equals 1, right? Of course, you can write initial state of Amongo and for length equals to 2. And length small equal to n, length plus plus. And we'll say for int j equals to I equals 1, I plus length smaller equal to n, I plus plus. So in this case, we'll have int j equals I plus length minus 1, right? So we are going to iterate the for int k. So that this is the last blooms which we left, right? So we'll see for every ij. So what is the last k? In this case, all of this has been on the left has been birthed out, on the right has been birthed out. So we just iterate the last one, right? So for every k equals I, k small equal to j, k plus plus, right? So we'll have we'll add this scope. We'll have left, middle, and part and right, right. So we'll have the middle part first. So we'll say if this is I equals 0, right? Then it is 1. Otherwise, it will be nums minus 1 multiple by nums k multiple by if j equals n minus 1, then it is 1. Otherwise, it will be nums j plus 1. So that this is the middle part, right? And also, if we'll see the left part, right? If k plus 1, if k is greater than I, okay, that means k doesn't equal I, or then we have the left part. We have current to the plus equal to dp I k minus 1, right? And I will say if k is smaller than j, we have current to the plus equal to dp. This is the right part. K minus 1 j. So we'll have dp I j will be maximum of max dp I j and the current. In the end, what we need is that return dp 0 and minus 1, right? This is k plus 1. Doing like this, we have actually we iterate length I, right? So this is like a iterate energy 2 for loop, and that the k, which will be the divider, right? So we have 3 for loops, so it will be O n cubic O n power 3 time complexity, and the space is an O square space complexity, right? And Python code should be very similar. We're going to have length equals int n equals length nums, and we're going to have dp with 1 multiplied by n for in range n, right? So we talk about the initial state, right? Because it is already, we can iterate for length equals to 0, right? So we can consider bloom I minus 1, right? Or we don't we can consider do not burst any blooms. Then the initial state is 0. We can also consider like that, right? Oh, and so the for L in range from 1 to n plus 1, and we'll say for I in range this n minus length L plus 1, right? Because the L, if L is 1, right? So I will be range n. So should be NL minus L plus 1. So we'll have J equals I plus L minus 1, right? So for K in range I to J plus 1, because this is inclusive for the we are using inclusive. Then we'll have current we have, for example, we have this left equals 1 if I equals 0, else nums I minus one, right? Right equals to one. If j equals a minus one, else nums j plus one. So current will be left multiplied by nums k multiplied right. Um, so I say if k plus greater than I, right? But Python actually, if we don't write this, so it is fine, right? Because uh, dp, I mean dpi, mm, I k minus one, right? Plus left plus dp k plus j, right? Because for this one, if this is uh k plus or minus one is smaller than I in Python, I think this is zero. We can so we'll have dpij equals max uh dpij in current. In the end, we just return dp zero and minus one. Auto range k plus one. Then but we still have needed this, right? So if k greater than I, we have dp current plus equal to this. I still write this kind of formula. And say if k is smaller than j, we have current plus equal to dp k plus one j. And we done this, need this. Current. So firstly, we should have current equals left followed by nums k multiplied by right. Okay.